In this video, we're going to be working AP Pre-Cal Homework 3.2, which is mostly about rational inequalities, but also about the behavior of a graph of a rational function near a vertical asymptote. But first, we're going to get in and solve some inequalities. So first one's x plus 1 over x minus 5 is less than or equal to 0. So the key thing for us is going to be identifying our key numbers and then, making a number line so we can make a sign chart that's divided up at those key numbers. So the key numbers are going to be the zeros of the numerator and the zeros of the denominator after the inequality has been set to 0. Okay, notice right here it's been set to 0 already for us, so we don't have to worry about that. We've already got what we need. We're going to say our key numbers are going to be x equals 5, the zeros of the denominator, and x equals negative 1, the zeros of the numerator. Okay. Now we're going to go in, we're going to get a number line. And this is one situation where we're going to have to make a number line because we don't really know what the graph of this thing looks like. Even if we did, it's not that great to sketch, and so we're going to be best off using a sign chart here. So our key numbers are negative 1 and 5. Then we're going to take a representative from each subinterval and use it as a test point. So something between negative 1 and 5 would be x equals 0. So at x equals 0, I'm having 0 plus 1 over 0 minus 5, that is a negative number. So we put a negative here. Something bigger than 5, I don't know, like maybe 10. When x is equal to 10, I'm going to have 10 plus 1 is 11 over 10 minus 5 is 5. That's going to be a positive number. And then something more negative than negative 1, like, I don't know, maybe negative 2. So I don't know if that's still on a shot, not quite. Zoom out a little bit. Okay, when I plug in x equals negative 2, I'm going to get negative 2 plus 1 is negative 1 over negative 2 minus 5 is negative 7. That's also going to be positive because it's negative over negative. Okay, then after that, I go and I'm going to, because this is less than or equal to 0, I'm going to label the zeros. Okay, the zeros, they come from the zeros of the numerator, so it's going to be x equals negative 1. So it's a place where we're equaling 0. X equals 5 is not a place where this fraction equals 0. This fraction is undefined at x equals 5, so I'm going to put an open circle there. Okay, I'm looking for where this thing is less than or equal to 0. Okay, so that's negative, and so it's going to be in the middle here. I'll say, all right, that's between negative 1 and 5, including negative 1 and not including 5. If we're going to write this in interval notation, it would be negative 1 to 5, like that. And this is a situation where it does matter, right? Increase, decrease, concave up, concave down, those intervals, we're not too concerned if you're going to include the endpoints or not. But this, it does matter because at x equals 5, the fraction is not defined, so we can't say it's less than or equal to 0. This next one is not already factored. It's set to 0, but it's not factored for us, so we're going to need to do that. Start by saying, all right, I think in the top I've got x plus 3 times x plus 1. In the bottom I have an x minus 1. I'm interested in where that's positive. Okay, so I'm going to think about my key numbers. Those are going to be x equals negative 3, x equals negative 1, and x equals positive 1. The zeros of the numerator and the zeros of the denominator are all going to be key numbers for me to solve a rational inequality. Okay, so I'm going to make a number line, label it with my key points. Oh, whoops, that wasn't right. It was negative 3, not positive 3. So it's going to start off with negative 3, then negative 1, and then x equals 1. And then I'm going to choose a representative between negative 1 and 1. I'll choose x equals 0. And when I plug in 0, I'd get 0 plus 3 over 0 minus 1, and that's a negative number. Okay, so I'm going to put negative there. And now we can do the same type of analysis we did with polynomials, right? Look at the multiplicity of these zeros in the numerator and the denominator, and if it's going to be a single root, we will see a sign change. At a double root, even in the denominator, like a double asymptote, we'll see togetherness at the asymptote. I'm not sure if that might have been part of your Algebra 2 class last year. It was not part of mine. We didn't look at 1 over x squared all that closely. I think we might have graphed it once on Desmos, but I don't see any double roots when I factored it up, so I'm going to see sign changes here. We can just maybe test that by thinking about what would happen if we plugged in, like, I don't know, negative 10. And I'd get negative over negative. Wait a second. Well, yeah, because I didn't alternate the sign right there. Okay, that'd be a problem. Okay, so sign changes at a single root, negative to positive, then positive to negative. All right. So then if I'd plugged in something like -2, I'd get -2 plus 3 is a positive number, but the other two factors, the x plus 1 and the x minus 1, would both be negative. And so negative over negative is positive. Okay, so yeah, I think next step, label the zeros. Now we're interested in where this is greater than 0. So we're not going to be including any of these points, okay, because at each of these intercepts here, or I probably shouldn't call them intercepts, key numbers is what I'm calling them, fractions either equal to 0 or it's undefined. Neither of those is greater than 0, so I'm going to label all these with open circles, and we want it greater than 0, so it's going to be through here and also out here. All right, so that's going to be -3 to -1 union 1 to infinity. Right, that one's factored for us, so it should be pretty easy to find the key numbers. It's going to be x equals -1, zeros of the numerator, and the zeros of the denominator, x equals 2 and x equals -4. Okay, -3, that's not going to contribute anything to my key numbers because it's not a 0 of the numerator or the denominator. If I plugged in -3 for x or 3 for x or even 0 for x, okay, that's another common error, I wouldn't get back 0 in the numerator or the denominator, so these are not key numbers. Okay, it'll probably just affect, like, the signs of these things, because, this one looks a lot like the last one we did. Okay, so -4, -1, and +2. But it'll probably just, like, come back with the opposite result because of that negative multiplier outside. Or maybe it'll be the same result, like, basically I'm saying this interval and that interval, because we're looking for where it's less than 0. I'm not totally sure how that's going to go. Choose a test point. I'm going to choose x equals 0, like plugging in x equals 0. That's going to return me -3 times 0 plus 1 divided by 0 minus 2 times 0 plus 4. That's going to be a negative over a negative. That's going to be a positive number. And all of these are single roots, so I'm going to see a sign change at every key number. And then I'm going to say, all right, I'm looking for where it's less than 0. So I'm not going to be using any of these endpoints. Less than 0 is going to be through here and also out there. All right, so that's from -4 to -1. Also from 2 to infinity. All right, d is one we will need to factor, but already set to 0. So maybe sometime soon we'll have one that's not set to 0. Those are a little more interesting, but also kind of a little more annoying. So I think I'll be happy to just, stick to these for a while. All right, my key numbers are going to be x equals 3, obviously from the numerator. And then the denominator, I think we can look at the denominator. We know how it factors, or we could see what will cause it to be 0. I don't think it's too much for us to just say, all right, that's going to be x equals plus or minus 2. Here I'm plotting the zeros of the numerator and the zeros of the denominator as equals, and then I'm going to use a test point. I'm going to find x equals 0. If that's not an endpoint, I'm going to use that. X equals 0 in the original fraction would give me -3 over -4, which is a positive number. Okay. All of these places would be single roots, either of the numerator or the denominator, because the denominator, I didn't write it, but I probably should. The denominator factors to x plus 2 and x minus 2, and each of those is a single root. So I'm going to see a sign change at each key number. So if I'm interested in where this is greater than or equal to 0, all right, I got to find the zeros. The 0 is at x equals 3. Okay, the other two are vertical asymptotes, so I'm going to not include those in my answer because that fraction's undefined at a vertical asymptote. It's definitely not greater than or equal to 0. Even if you were of the opinion that it's going to positive infinity, okay? Because that would be representing, like, it is going to be going to positive infinity as x approaches -2 from the right side, which is what we're going to get into here in a couple minutes. But that's for x values to the right of -2. At -2 itself, fraction's undefined, and that's not greater than or equal to 0. So I've got -2 to 2, not including either endpoint, or 3 to infinity, including 3. With this one, we're going to need to do some factoring. I think in the denominator, what's that? That's going to be x minus 5 times x plus 3. All right, so this is interesting. I don't know that we have this in the examples in the notes. I can't remember it, and I haven't recorded that video yet. So I don't know if there's a hole in, like relating to the rational inequality. So I'm going to assume that we haven't seen this before. And I'm going to cancel, or actually, I'm not. I'm not going to cancel. I'm going to consider x equals 5 as a key number, see what happens, and then maybe in the future, if I see a hole, if I didn't see a sign change or if nothing was happening there, then maybe I might think about excluding the x coordinate of a hole. So the key numbers this time are going to be x equaling 5 and x equaling -3. I am going to be really careful with the sign chart. I'm not going to assume anything about what's happening at x equals 5. Because we know there's a hole in the graph, and that probably, and because the numerators, or the degree, the multiplicity of the 0 at x equals 5 and the numerator and the denominator are equal, both single roots, we know there's going to be a hole in the graph. And it's otherwise going to look like the graph of 1 over x plus 3. And I don't think anything special is happening to the graph of 1 over x plus 3 at x equals 5. Okay, I think that's what we're going to find. So I guess it would be a key number because we would have to exclude it if, say, we found, suppose we found both of these were positive. We'd need to exclude x equals 5 from our solution region. I guess that does make it a key number. But we're probably not going to see a sign change unless there was an extra factor of it in the numerator, which is kind of what we saw in the last lesson. Anyway, let's get a test point. So at x equals 0, I'm going to plug in and I'll get -5 over -15. And that's a positive number. To the right of 5, like 100. Okay, I'm going to want to use the factored version for this one. X equals 100, I'm going to get 100 minus 5 is 95, very positive number, divided by 100 minus 5 is 95 again, and x plus 3 is definitely going to be a positive number, that's positive. And then when x is more negative than -3, like x equals, I don't know, -4, okay, yep, still got room. I'm going to plug into the factored version. -4 minus 5 is a negative number, divided by -4 minus 5 is still negative, and -4 plus 3, another negative. So I've got a negative over a positive, that's negative. We're interested in where x is strictly greater than 0, so we will not be including any of these. But we will like this. All right, so I think the moral of the story here is for like a true hole in the graph where it's, same multiplicity on top and bottom, it's probably not going to impact the sign chart, but it is going to be an x value that we need to exclude from our solution region if it was otherwise going to look like it was in there. Okay, so my solution will be -3 to 5, and then 5 to infinity. All right, looks like this one's got the same thing going to happen. So if I factor the numerator, I'm going to get x plus 4x minus 3. Divided by x plus 3x minus 3. Interested in where this is less than or potentially equal to 0. All right. So what I'm going to do, I'm going to say, all right, I can see that these factors are canceling, this x minus 3, and so I am going to, kind of label my key numbers and say, all right, I'm going to have x equals -4, x equals -3, and then x equals +3, but I'm not going to, divide my interval there. I think I'm going to say at x equals 3, I'm going to have an open circle. I'll show you what I mean. So I'm going to draw my number line. And then when I go to label it, I'll say, all right, -4 here, -3 over here, and then I'll put 3 as like a whole preemptively, but I'm not going to divide my interval that way, okay? Because I know the sign's not going to change there unless I had a leftover factor on top or on bottom. Kind of for reasons that we got into in the last lesson. Okay, but I'm going to choose my test point will be x equals 0. So when x is equal to 0, I plug into the fraction, I get -12 over -9, which is a positive number. Okay, I know the sign won't change there, it's just a regular whole. And then, but the sign will change at these other x values because these are single roots of the numerator or denominator. Okay, and if we wanted to check ourselves just to make sure that was right, we could plug in like, I don't know, x equals -10 for that far left edge and see what happens. I would get, use the factored version. -10 plus 4 is -6. Okay, I'm going to imagine that I had canceled off those factors because at -10, that's not x equals 3, so that's not really going to be impacting. It's just going to be multiplied by 1. Over x plus 3, -10 plus 3 is -7. Negative over negative, that's positive. Makes sense. All right, so where it's less than or equal to 0. Okay, where is it equal to 0? It's equal to 0 at the zeros of the numerator. X equals 4. And then we would think x equals 3, but that's a hole in the graph, so it's not actually there. Okay, so from here I'm looking for it's less than or equal to 0. X equals -3 is a vertical asymptote, so we're not going to include that. And we just want less than or equal to 0, so there it is. -4 up to -3. That would be including -4, not including -3. All right, now we've got one that's not set to 0. So I guess I know that I will have gotten to it in the lesson when I get around to recording that or delivering the lesson to you in person or in the past or whenever that is. But we're not going to just be able to multiply both sides by x plus 3. Now you can, I'm not saying it's algebraically impossible, but you have to split it out into 2 cases, and in my opinion that's really not worth it, because y'all are pretty strong with algebra. You can turn the 1 into a fraction and then combine them under a single denominator, and then just use the same technique we've been using for all the rest of the rational inequalities. So we just got to try to set it to 0. So -2 over x plus 3. I like this one starting off with 1 because it's really easy to think of how we would write 1 as a fraction with denominator x plus 3. It'd be x plus 3 over x plus 3. And then, I mean, we could subtract the thing on the right from both sides, or we could add the -2 over x plus 3 to both sides, and that's kind of like what I like the look of. So I'm going to say 0 is less than or equal to x plus 3 over x plus 3 plus 2 over x plus 3, which is like saying 0 is less than or equal to x plus 3 plus 2. And I'm going to write out all the steps, and then I'm going to kind of collapse it down to what I think we actually need over x plus 3. And I could combine like terms and see that 0 is going to be less than or equal to x plus 5 over x plus 3. All right, so that's really all we're going to need is the resulting inequality. So I'm going to, try to identify my key numbers. Oh, whoops, whoa. Let's see. Yeah, there we go. There they are. And I'm going to say, all right, those are going to be x equals -5 and x equals -3. Myself a number line, label it with those key numbers. Then choose a test point. I'm going to choose x equals 0. That's over there. So at x equals 0, I'm going to get... Okay, I'm going to use this expression because that's what I'm kind of like comparing to 0. So I'm going to say 0 plus 5 over 0 plus 3. That's 5/3, which is a positive number. And, both of these zeros, x equals -5 and x equals negative 3, the zeros of the numerator and denominator respectively. These are both single roots of the numerator and denominator, and so I know there's going to be a sign change in each of them. Okay, and then we're looking for less than or equal to, so identify which of these is an actual zero of the fraction. Okay, x equals negative 5 is an actual zero, but x equals negative 3 is a vertical asymptote. So we would potentially include x equals negative 5, but we will definitely not include x equals negative 3. And then the other thing we need to be careful about is looking at this, right? We're looking for where the fraction is going to be positive, right? Even though it says less than or equal to, because that 0 is less than or equal to the fraction. Well, if 0 is less than or equal to the fraction, that means the fraction's probably got to be positive. Maybe it's equal to 0. So I'm going looking for where it's positive, and oh, I don't want a highlighter, I just want a red pen. So I go over here, and then over here, I'm also seeing positive. So I'm going to have two intervals. It'll be negative infinity up to negative 5, but including negative 5, union 3 to infinity. All right, with this one, same idea. I'm going to rewrite. It's a highlighter, I want a pen. So 2x over x minus 2 is greater than or equal to 3 times x minus 2 over x minus 2, right? If we want to get that common denominator, we got to multiply the original thing by 1, just, the proper form of 1. So that's going to be x minus 2 over x minus 2. All right, then I'm going to subtract from both sides. Okay, so I'd say 2x over x minus 2 minus, then maybe I'll also distribute the 3 over the x minus 2, so I'd have like 3x minus 6. Right, so I'm going to need to be careful doing that subtraction, right, because that's where errors can occur. And I'm interested in where this is greater than or equal to 0. Okay, then I'm going to combine these, so I'll have 2x minus 3x minus 6, all divided by x minus 2. That's 2x minus 3x plus 6, if I'm subtracting the negative 6, divided by x minus 2. And let's just go off to the side. Negative x plus 6, or maybe I'll call that 6 minus x, divided by x minus 2. That needs to be positive. All right, or equal to 0. So I'm going to take that, and I'm going to just keep the end result. And so now I've got it in this form. It's pretty easy to see what my key numbers are. They're going to be x equals 6, because that would make the numerator equal to 0. And x equals 2, which would make the denominator equal to 0. Make a number line. Label it with the key numbers. Use a test point and get to work. So I go to the new version, the version that's set to 0. Say 6 minus 0 is 6, that's a positive number, divided by 0 minus 2, it's a negative number, that's negative. Right, so negative, and x equals 2 is a single root of the denominator, and x equals 6 was a single root of the numerator, so I'm going to see a sign change at each of these places. I want to know where this is greater than or equal to 0. This fraction is going to be equal to 0 when x equals 6. So that is a potential included point. In fact, it will be an included point because I know it solves that inequality because it's equal to 0. Then at x equals 2, that's going to be a vertical asymptote on the fraction, and so it's not going to be equal to 0 because it's not going to be defined at all because it has division by 0. I was also going to mention that, yeah, x equals 6 is the type of thing that if we plugged it in, I'd get 12 over 4 equals 3. So that's like why it's one of the zeros, one of the edge points, because, on the original inequality that's written, that's typed, you can see that makes it equals. Okay, so that's going to be the very edge of the interval that works. Okay, we want greater than or equal to 0, so that'll be through here. So I'm going to say starts at 2, ends at 6. We're going to include 6, and we're not going to include 2. So that's my solution. All right, I've got 4 more of these, and I think I was originally going to like publish an extra practice set for rational inequalities, but I really think that if a person needed more practice, they could just go right back to these and just work them on a different sheet of paper and get the same kind of practice because this is pretty comprehensive. So what we're going to do, we're going to do the same process we've done the last two times. 3x plus 1 over x plus 4 is greater than or equal to, well, we'll write 1 as x plus 4 over x plus 4. Okay. Then I'm going to subtract one of the fractions from both sides. I'm going to just subtract x plus 4 over x plus 4 from both sides. Minus the x plus 4 over x plus 4, because that's 1. As long as x is not equal to negative 4, but if x is equal to negative 4, we're already in trouble because the expression on the left isn't defined, so that's kind of the logic there. Is 1, then I'm going to say, all right, well, let's actually combine them with a single denominator. 3x plus 1 minus x plus 4, all divided by x plus 4. And then I distribute the negative. Wait, oh, made an error up here. Called that 1, that's going to be greater than or equal to 0, right? Because if I subtracted x plus 4 over x plus 4 from both sides of that inequality, I'd be left with nothing on the right side. Right, so this is greater than or equal to 0. And then that's going to be 3x plus 1 minus the x and minus the 4, because I was subtracting the x and the positive 4. And I'm divided by x plus 4. All right. And then looks like what I'm going to be left with is 2x minus 3 over x plus 4. And we want to know where that's greater than or equal to 0. All right, now that I've got it set to 0 after some algebra, I can identify that my key numbers are going to be x equals negative 4. That's definitely the 0 of the denominator. And then also x equals, well, whatever would cause 2x minus 3 to equal 0. It looks like 1.5 to me, but I'll just make sure. X equals 3 halves. Yeah, x, you could write it as 3 halves. You could write it as 1.5. Since we're going to be doing some numerical analysis here, I'm just going to write it as a decimal. And that's perfectly fine. All right, so draw my number line. Label it with my key numbers. Then I'm going to choose a test point and choose x equals 0. I'm going to test it against that. Let's say, all right, 2 times 0 minus 3 is a negative number, divided by 0 plus 4 is a positive number. So I'm going to have negative here. X equals negative 4 is a single root of the denominator, so I'll see a sign change. And x equals 1.5 is a single root of the numerator, so I'll also see a sign change there. I don't know where this is greater than or equal to 0, so I find where is it equal to 0? That was at x equals 1.5. And it is undefined at x equals negative 4. That is not what I was interested in, right? I wanted to know where it was greater than or equal to 0, so that's going to be out here and also over here. It's positive, greater than 0. All right, so that's negative infinity up to negative 4, but not going to include negative 4. Union 1.5, but we're going to include 1.5, so I need a square bracket there. Up to positive infinity. This one looks very similar, so I'm going to say, all right, I've got x squared minus x. Maybe the factoring will work out on this one. I'm very hopeful. Less than or equal to, all right, I'm going to call that 6 times x minus 2 over x minus 2, because that would be equal to 6 anytime x was not equal to 2, but if x was equal to 2, the whole thing is not going to be true because the expression on the left, like right here, that would be undefined. Okay. So I'm going to subtract the 6 times x minus 2 over x minus 2 from both sides. Get x squared minus x over x minus 2 minus, Okay, I'll distribute the 6. That'll be 6x minus 12 over x minus 2. And that's going to be less than or equal to 0. Then I will combine these things with a single denominator. So x squared minus x minus 6x minus 12. Okay, and then I'll say, all right, I'll distribute the negative. Minus 6x plus 12 divided by x minus 2. And okay, I need to combine these like terms. Oh, okay, yeah, it is going to be factorable. I was kind of nervous there. I'm going to have x squared minus 7x plus 12 over x minus 2. That's going to be less than or equal to 0. And then from this one, I can factor the numerator. That'll be x minus 4 times x minus 3, all divided by x minus 2. We're interested in where that is less than or equal to 0. Hey, and that'll be great for us. We've got our key numbers easily visible. All the rest of this algebra work is not going to be anything we need. So we'll just kind of show our result over here, but you will need to be able to do this, right? Obviously for the equivalent problem on the quiz. They're not going to all just be already set to 0 for you. You will want to show your work on that, not necessarily because we're grading it, but because if you were to make an error, it would be helpful to identify where you had made an error. Well, I forgot to list my key numbers. Right, those will be x equals 2, x equals 3, and x equals 4. Then zeros of the numerator and the zeros of the denominator. So I'll label those. Use a test point. I'm going to use x equals 0. When I plug in, I have negative 4 multiplied by negative 3, all divided by negative 2. So that's a positive over a negative is negative. And then x equals 2 is a single root of the denominator, so we'll see a sign change. X equals 3 and 4 are both single roots of the numerator, so those will both correspond to sign changes as well. And then I'm looking for less than or equal to 0, so I find the actual zeros, and those are x equals 4 and x equals 3. And then x equals 2 is a vertical asymptote. And so I'm looking for where this thing is less than or equal to 0. That'll be here. All right, that's what I have to do. Okay, so that's going to be x is less than 2. Also, x is between 3 and 4, but including both. Realize I don't even write my answer in interval notation, and I wouldn't want anybody to think that if they wrote it in inequality notation, they'd be wrong. I just don't think I necessarily need to do both every time. Union 3 to 4. All right, now these last two have a little bit more going on, right? They've got fraction less than or equal to greater than or equal to fraction, and they have different denominators. So we're going to have to do the same thing I've been doing, set it to 0, combine using a single numerator. I'm going to start off by saying, all right, well, 3 over, I'm going to maybe start by subtracting this time. And maybe that's what I should have been doing all along, but okay, so then I'm going to need to take the 3 and multiply it by x minus 3, the opposite denominator. So that's what, x plus 4, x minus 3. Minus the 1, I would need to multiply by the opposite denominator on top and bottom. So I'm really multiplying by 1, so I haven't changed the value of the fraction. This is greater than or equal to 0, so I've got, I distribute the 3 over the x minus 3. And then I'm going to do the subtraction. I'm tired of writing two denominators. And we're definitely not going to distribute out the denominator because we're, kind of going to want this thing factored on top and bottom eventually. So then when I actually do the subtraction, it'll be minus x minus 4. So back up here, 3x minus 9 minus an x minus 4. X plus 4 into x minus 3. I'm interested in why this is greater than or equal to 0. Okay, 3x minus x is 2x. Negative 9 minus 4 is negative 13 over x plus 4 and x minus 3. All right, so this is going to be a useful way of writing this inequality. All right, so next, identify key numbers. So x equals negative 4, x equals 3. That's a little close. These are zeros of the denominator. They correspond to vertical asymptotes. These are definitely going to be key numbers. Then anywhere where 2x minus 13 would equal 0. Maybe you see this. It looks like 6.5 to me. 2x equals 13 divided by 2, x equals 13 divided by 2, or 6.5. And again, I'm going to use the 6.5 because we're doing numeric analysis here. So I'm going to get rid of that and just say, all right, key number from the 0 of the numerator was x equals 6.5. Draw this thing, label it with my key numbers. Just choose a test point. I'll choose x equals 0. And then if I was to plug into my simplified version of the inequality, I'd get 0 minus 13 is a negative number, divided by 0 plus 4, multiplied by 0 minus 3. So it looks like negative over negative, that's going to be a positive. Okay, and then all of these factors appear once in the numerator or the denominator, so I'll see a sign change at each key number. And then think about the zeros. Can't forget that. Okay, the real 0 was at x equals 6.5, because the other two were vertical asymptotes. Okay, and I want greater than or equal to 0. So I've got greater than through here and greater than out there, equal only at 6.5. So that's negative 4 up to positive 3, union 6.5 to infinity. All right, and the last of our polynomial inequalities, I was looking at this, I said F. I was like, I feel like I've done way more than 5 of these already, but evidently we messed up on the numbering. And, all right, so 6 over x squared minus 4 less than 1 over x minus 2. All right, so I'm going to start by subtracting, maybe factoring the x squared minus 4, so it's a little clearer to us what we need to do. X plus 2x minus 2 minus 1 over x minus 2, but I'm going to just go ahead and multiply by the opposite, or the factor I need to have an identical denominator, right? I need that x plus 2. So we're multiplying the 1 over x minus 2 by 1, but just the right form so we can get the right denominator. All right, then I'm going to have 6 over x plus 2x minus 2 minus the x plus 2, and I'm going to actually combine those with a single denominator. We've been doing that quite a bit lately. I don't think you need to see all the extremely detailed algebra steps. I don't really like the way this looks. I'm going to move that. It still doesn't look great. We want this to be less than 0. I kind of left that off. Okay, so 6 negative x, so 6 minus x, I have negative x. 6 minus 2 is positive 4. All right, and so that's the expression of the inequality that I'm going to want to use for my number line. Numbers of this inequality are going to be x equals negative 2 and x equals positive 2, because those are zeros of the denominator. And also x equals positive 4, because that's a 0 of the numerator. And then I'm going to draw the number line, label it with those 3 points. Negative 2, oh, I don't need it to be a shape though. Negative 2, 2, and 4. So x equals 0 happening in there. be negative 0 plus 4 is a positive number divided by 0 plus 2 and 0 minus 2. So that'll be a negative there. Okay, all of these factors appear once. They all have multiplicity 1. So I know I'm going to see a sign change at each key number. Okay, so I've got positives here and a negative out there. Okay, thinking about the zeros, I don't need to because this is strictly less than 0, so I won't be interested in including any of the key numbers. Less than 0 is negative. So I'm going to choose those places. And I'll say, all right, negative 2 to 2, and also when x is greater than 4. All right, that was a lot of rational inequalities, 40 minutes of them. And so we're ready to move on, aren't we? So we're going to compute the limit. And so just I need you to remember at this point, I think the types of limits that we know about are polynomial function and behaviors. And those are x approaches infinity, and it's a polynomial. Last time we got the limits that represented a hole in the graph, and that was where we saw a factor canceling off in top and bottom, or maybe we saw 0 over 0 when we tried plugging in. And today the new thing is the one-sided limits near a vertical asymptote. Now what I did was I made sure to, on some of these that were a hole, I still made it one-sided because I don't want you to assume if I see a one-sided limit, it's because they're asking me about a vertical asymptote and it must be infinity or negative infinity. That would be a really easy error to make. I don't want you to make that. Okay, so what we're always going to try first is plugging in. And I'm going to say, all right, as x approaches 1, I'm going to have 1 plus 1 over 1 minus 1. That's 2 over 0. If I see non-zero over 0, that's a vertical asymptote. And then my job becomes do some sign analysis to determine if I'm approaching positive infinity or negative infinity. So I've got, a number line labeled. The key value here is x equals 1 because that's what I'm approaching. I like to draw in a little dotted line like for the vertical asymptote. Okay, since it's x equals 1, that looks like a dotted line. All right, so I've got x equals 1 there. We're approaching from the positive side. So that means from the right. And that means I'm going to be interested in choosing a number that's greater than 1 for my test point. So I'm going to choose, I think it's probably safest that we choose something very close by, like 1.1. But you just need to not go across any of the x values that would be considered key numbers if we were solving a polynomial inequality. That's what I'm going to say. I'm going to choose x equals 1.1. So when x equals 1.1, I'm going to have 1.1 plus 1 is 2.1, which is a positive number, divided by 1.1 minus 1 is positive 0.1 is also positive. So if I take positive and divide by positive, I'll have a positive number. So I'm seeing positive here. That means that the graph of y equals x plus 1 over x minus 1 is somewhere up here. And it's approaching a vertical asymptote, so I know I'm approaching positive infinity. So I'll say the limit as x approaches 1 from the positive side of x plus 1 over x minus 1 is positive infinity. All right, on B, I'm going to try plugging in first, and I'm going to get 2 from the negative side. I'm going to have 2 squared is 4 minus 4 times 2 is 8 over 2 minus 2. Okay, that would be negative 4 over 0. And that's not good. That means I'm sitting on a vertical asymptote. And just like the last one, my job is to figure out, am I going to positive infinity or negative infinity? So I'm going to do a little sign analysis near x equals 2. All right, here's x equals 2. I'm going to be interested in the left side of x equals 2 for my test point. So maybe I'll choose 1.9. Great. All right, that's as good as I got. That might be a little too zoomed in there. Okay, when x equals 1.9, I'm going to have, we're going to need to factor this because I don't think it's immediately obvious that 1.9 squared minus 4 times 1.9 is going to be a negative number, which I'm not even sure about that myself. So I'm going to factor the thing. I'm going to say, all right, that's x times x minus 4 divided by, yeah, it's going to be negative, divided by x minus 2. Okay. And when I plug in x equals 1.9 to that, well, 1.9 is a positive number. 1.9 minus 4 is clearly negative. And 1.9 minus 2 is also a negative number. So I'm going to have negative over negative. That's going to be a positive number. So if I'm positive above the x-axis, while also approaching a vertical asymptote, just like we said last time, that limit's going to come back infinity. Something like that. And so I'm going to say this limit, as x approaches 2 from the negative side, x squared minus 4x over x minus 2, that's also going to be positive infinity. All right, C is the limit as x approaches negative infinity. Okay, first thing, we see that x approaching negative infinity, and we need to think in behavior. But then we look at what we're taking the limit of, and it's a polynomial. Okay, so determining the end behavior of a polynomial is going to be like we're going to make that determination based on the high degree term. So I'm going to say this is a 5th degree polynomial, which is an odd degree, and the leading coefficient is negative 1/4. And what's important about that is that it's negative. Okay, so as a result, it's going to look like y equals negative x cubed, at least on the outsides. Okay, and so as a result, as I'm thinking about x approaching negative infinity, it's over here on the far left side, I'm going up. So this limit is going to be positive infinity. All right, this next one, okay, I thought we were going to get one with there was a hole in the graph, but I'm sure that's going to come eventually, but it's not happening here. But as when I'm not seeing x approaching infinity or negative infinity, I always try plugging in the x value just to see what happens. Because every once in a while, it'll just come back something that's not got a 0 in the denominator. And, in that case, the value of the limit is just what we would expect it to be, what we got when we plugged in. So that's going to be 0 squared plus 3 zeros. That's 1 over 0. I'm not going to say it's equal to 1 over 0, and that's not something that we really need to be super worried about in pre-cal, but will be a big deal in calculus, these presentation or linkage errors. I'm just kind of using arrows to indicate, like, hey, I'm just like trying to see what would happen here. Okay, I got 1 over 0. That means I've got a vertical asymptote. But you probably heard me say in class before that equals is a relationship that's defined between two numbers, right? Like two real numbers or two complex numbers or something. But something that's undefined, like 1 over 0, that can't be equal to anything because it's not a number. Right, so we've got a vertical asymptote, do sign analysis at x equals 0. So we've got x equals 0 there. And we're approaching from the negative side. So I'm interested in values to the left of 0, like to the negative side. So I can do maybe negative 0.1. When x equals negative 0.1, I'm going to have 1 minus negative 0.1. Okay, I think to do this sign analysis, we're going to have the numerator and denominator fully factored. I'm kind of realizing that now. I feel like, I don't know. We don't do this a whole lot in my calculus class, and I guess the ones that we do work with are, I guess they're factored, or they might be actually relatively simple. They might be more like 1 over x squared plus 3x, right? Like what's going to happen there is x approaches 0 from the negative side, so that it wouldn't, it wouldn't be something. I guess that's that x squared plus 3x. I don't know. I don't remember having to do this in the past, but. Okay, and when I'm doing that, I'm looking at this, I'm plugging in negative 0.1, numerator is going to be positive. Denominator is going to be, well, negative 0.1 is a negative number, and negative 0.1 minus 3 more would be even more negative. So I've got positive over what will become a positive, that's going to be positive. Okay, so over here, it's just been positive infinity every time. I was doing that in red before. So I saw it was positive. And if I'm positive while approaching a vertical asymptote, that must mean I'm approaching positive infinity. So the limit as x approaches 0 from the negative side of 1 minus x over x squared plus 3x, that's going to be positive infinity. All right, on this one, x is approaching -1, so I'm going to want to try to plug that in. If I was to plug that in, I'd get -1 over 0. That means I've got a vertical asymptote. I will do some sign chart analysis around x equals -1. I'm approaching from the positive side, so my test point will be a little bit greater than -1. So a little bit to the right of -0.1 on the number line would be like -0.9. Okay, when x is -0.9, I'm going to have a negative number on top, and -0.9 plus the 1 will become positive. Of negative over positive, that's negative. Okay, so I'm going to say, all right, negative over here. That means that the graph of y equals x over x plus 1 is, I don't know, somewhere down here below the x-axis while approaching a vertical asymptote. So that means that this limit has got to be negative infinity. So the limit as x approaches -1 from the positive side. That is negative infinity. All right, this last one here, I've got x plus 5 over x squared minus 4. Okay, I can see that the denominator is factorable, so I think I'm going to actually just do that immediately. I haven't been doing that on the other ones, but x approaches -2 from the negative side, x plus 5 over x plus 2, x minus 2. Now, we can see that as x approaches -2, that's going to cause this factor right here to go 0. And so as a result, I'll have -2 plus 5 is 3 over 0. That means I've got a vertical asymptote. My job is to figure out if the fraction is approaching positive infinity or negative infinity. We'll do that with sign analysis. Center our discussion at x equals -2, draw in that there's a vertical asymptote there. Then we can choose something. Okay, we're interested in the negative side of -2, so values to the left of -2, like, I don't know, maybe -2.1. Then when x equals -2.1, I'm going to get -2.1 plus 5. It's a positive number. -2.1 plus 2, definitely positive, and wait, no, that's not true. It was -2.1. Okay. Yeah, because it's -2.1 plus 2 would be -0.1, and then -2.1 minus 2 would definitely be negative. Okay, this is going to be positive. Okay, we've got to be very careful on that sign analysis, right? Because if we get one of the things wrong, it's probably going to, mess up our result unless we made some sort of complementary error. Okay, so that's approaching positive infinity. It's positive while approaching vertical asymptote. The value of the limit as x approaches -2 from the negative side of x plus 5 over x squared minus 4, that is positive infinity. All right, now here we've got another double graph problem. Okay, so f and g are shown in the figure below. Now we can see, probably don't have enough information on g to determine the leading coefficient. Yeah, I don't think we do, because all of the grid intersection points are also zeros, so we don't really know what the leading coefficient is. Moreover, that's not really going to be the point of this problem, right? We're going to be thinking about the zeros and their multiplicities. So I am going to label that x equals -2 right here is what I would consider to be definitely a single root, because the graph is passing through confidently, and kind of the same thing here. Single root, and these are all 3 single roots. Okay, so, oh, wait, I'm not interested in whole versus vertical asymptote on this one. I'm going to be interested in the actual, limit based on the positive negative behavior. I completely forgot. Okay, so h of x is f over g. So as x approaches 0 from the positive side, I'm going to actually kind of rewrite this limit. It's h, that's f over g, just had to make sure. This is going as x approaches 0 from the negative side. Okay, what happens to f? Well, f is going towards -2. And then as x approaches 0 on g, oh wait, not still visible, yeah. As we're approaching 0 from the negative side, I'm approaching 0 negatively. Okay, so I'd say 0, but it's a negative number. I'm going to talk to the other pre-cal teachers, ask them how they are kind of displaying their answer on this. But I'm seeing it's going to -2 over 0. I think what I'm going to actually write is it's going to be going to -2 over 0 as a negative over a negative. A negative over negative is positive, so this limit is positive infinity. Okay, so this problem is just like the ones I had previously solved, except without the algebra, right? We're going from a graphical perspective, but the same process holds true, right? I kind of think about what happens as x goes to 0. F's going to -2, g's going to 0, so I'm going to -2 over 0. That means I'm sitting on a vertical asymptote, and I'm realizing I see what I should have done here. Okay, at this point with the algebraic problems, I said, all right, I've got a vertical asymptote. I don't have room to write that. So I'm going to make a little sign chart for sign analysis. And then, think about it, x equals 0. I'm going to choose something a little more negative, like -0.1. Well, f of -0.1 is going to be near -2. -2 or something near, divided by, we determined that g was negative because the graph was like coming up towards that 0 there. And so negative over negative, that's a positive number. I'm up here, I'm going towards vertical asymptote. I kind of forgot to write that in, but I don't have much room. So this graph's going to positive infinity. Or the fraction, or h, yeah, h is going to positive infinity. All right, as x approaches 0 from the positive side, h of x. Okay, we've already determined it's going to -2 over 0. I didn't see any double roots in the original image, so it's probably going to be the opposite, but it's probably best we think a little more closely about it. So this is going to -2 over 0. So I know I've got a vertical asymptote. I'm actually just going to go over here to the same sign chart I made earlier, and I'm going to choose a point to the right of x equals 0. That would be x equals positive 0.1. So when x equals positive 0.1, I'm going to think, okay, well, f right here is still negative. To the right of x equals 0, I still have this. Okay, so to the right of x equals 0, I didn't get rid of that. To the right of x equals 0, maybe at x equals 0.1, I've got a positive number. So I'm going to report that. I'm going to go down here, and I've got, all right, f was negative and g was positive. Okay, so that's negative. And as a result, I'm going to say, all right, I'm down here, and then I'm going to negative infinity. So I'll say that the second one, as x approached 0 from the positive side on h, that was negative infinity. All right. As we approach -1, I'm going to just look and see, yeah, I'm going to be asked about both of these one-sided limits on h. So I'm going to do analysis of h. Yeah, f at -1 is -0 over here. I feel like, isn't it going to play out the same way? Oh, no, -1. Whoops. Yeah, so no, it's going from negative to positive, so it'll probably be the opposite, but we should probably do the analysis to make sure. All right, so as x approaches -1, just kind of zoom in. Maybe I'll just work off the graphs. I'm going to say actually, the limit of h of x as x approaches -1. That's going to -2 divided by 0. So I've got a vertical asymptote. Now my job is to figure out what's going on with the graph of h near x equals -1. But I can do that. So line, label the vertical asymptote. All right, and then I'm going to check on either side because I know that the problem is going to eventually ask me for both sides. All right, so I'm going to choose a number a little bit more negative than -1, so like -1.1, and then something a little bit greater than -1, that would be -0.9. Okay, then I'm going to plug these values in. H of x is going to be at -1.1. F is no, wait. -1.1, that's here. F is negative, G is positive. Okay, so I've got a negative number here. And then x equals -0.9. I'm going to kind of get rid of these marks there. X equals -0.9. F is negative, G is negative. Okay, so that's going to be a positive number. Okay, as a result, I know that the graph of h is going to look something like that, at least very near x equals -1. And so I'm going to say as I approached from the negative side, from the left, I was going towards -infinity, right there. Okay, so I'll say this limit is -infinity and this limit was +infinity. Okay, now we've got two more. Limit of j of x, which is the reciprocal. So I should probably clear out all these annotations here. Okay, it will not let me clear out that horizontal line, but maybe I'll just use it again, because I know I'm going to do the same analysis. J is g over f. J is having a vertical asymptote at x equals -2, because at x equals -2, I can see g is going to definitely be positive, right? It's going up there, so that's as good as I've got. And then f down there is negative, or is 0. So number over 0, vertical asymptote. So j of x as x approaches -2. So the limit as x approaches -2 of g of x over f of x. That's going to, I don't know, some unknown positive number divided by 0. So that means I've got a vertical asymptote. In x equals -2. So we'll say -2.1, -1.9. Because they're going to ask me about both sides, so I might as well just do all the work in once. Okay. So with this, let's see, when I plug in x equals -2.1, okay, g is going to be positive because it's going up there. I don't even know how, like we can't quantify how big it is at -2, but we definitely know it's positive. Okay, and then -2.1 over here, f is positive, so I got positive over positive. That's going to be a positive number. Okay, then with x equaling -1.9, okay, g is going to be positive, f is going to be negative. So I got positive over negative, so I know that the graph is going like that. And so I can answer those limit questions, right? From the right side, as x approaches 2 from the positive side, that's the one over here, I'm going downhill, so I'm approaching -infinity. Whereas as I approach -2 from the negative side, from the left, graph is going to +infinity. All right, and now the last problem here is compute the limit, and I think this is whole versus vertical asymptote. All right, so notice that if I'm approaching 5, so I want to just try plugging in 5. So that's approaching 0 times 1, or times 6, well, that's just going to be 0 over -2 times 0, that's 0 again. 0 over 0, possibly a hole in the graph. We need to factor and cancel. In fact, I'm not even going to say hole in the graph because I don't know that for certain. I mean, I do, but after factoring and canceling, then we would be certain. already factored for us. We're going to cancel here, and then we're going to try again. So this limit is equal to the limit as x approaches 5 from the positive side, and we do need to maintain that limit notation because that limit is not just equal to the fraction x plus 1 over x minus 2. That would be untrue, right? It would cost you an AP calculus. And I don't want you to get into those bad habits here. So it's equal to that limit, which now I think I can plug in 5, and I'm not going to get any division by 0, so that's 5 plus 1 is 6, divided by 5 minus 2 is 3, that's going to be 2. That's great. And then the last problem. Okay, yeah, over here, if I'm to plug in x equals 5, I'm going to get 10 times 6 is 60, divided by 5 minus 2 is 3 times 0. Oh, 60 divided by 0, that's a vertical asymptote. So I figured we'd wrap up with one more of these. No, that's not how you spell that. Asymptote. And now I'm going to do some sign chart analysis. Lots of sign charts today. But that's what we showed you how to do in the last unit. Even though, some of y'all didn't feel like you needed to use them all that often for polynomials. If you could just sketch a graph, that's fine. But for these, you can't just sketch a graph of these. We don't just know what they look like based on the, zeros and behavior. So, all right, vertical asymptote. We're approaching 5 from the negative side. So I'm going to be interested in something like 4.9. When x is equal to 4.9, this fraction is going to give me 4.9 plus 5 is positive, 4.9 plus 1 is also positive, divided by 4.9 minus 2, that's a positive number, that's 2.9, but 4.9 minus 5, that's a negative. Now if I have one negative, that's going to come back negative. For here, the graph's below the x-axis while approaching a vertical asymptote, so that means the limit is negative infinity. And that's all for this video. This was a marathon. Thanks for sticking with me. I really hope this helped.